In this video, we're going to study the first application of the principle of virtual work. There are three applications that we're going to study for the principle of virtual work. The first one is just for illustration. It shows that the principle of virtual work is equivalent to the equilibrium equations. And so we're going to show the first application as finding the reactions of statically determinate beams. The second application is finding displacements at specific points for linear elastic small deformations beams. And this application is used in structural analysis courses. The third application, which is finding approximate solutions, is the basis for the finite element analysis method, which is used for finding approximate solutions for the differential equation of equilibrium applied to a continuum. For the first application, finding the reactions of statically determinate beams, we know the equation of virtual work states that the internal virtual work expressed as EI, the second derivative of y with respect to dx1 squared, multiplied by the second derivative of y star, which is the virtual displacement with respect to dx1 squared, is equal to the external virtual work, which is the work done by the distributed load Q, and the external forces V2, V1, M2, M1 during the application of the virtual displacement and the virtual rotation. In this application, we're going to choose a displacement y star, a virtual displacement that satisfies that the second derivative is equal to 0, which means that the external virtual work would be equal to 0. So we choose a displacement y star that is a rigid displacement of the beam that ensures that there's no internal virtual work. And so, for example, let's look at the shown beam. The beam is of length L. A concentrated load of P is at a point that is A from the left and a distance B from the right. There are three unknown reactions, R1, R2, and R3. The equations of equilibrium state that the sum of forces in the horizontal direction are equal to 0, the sum of forces in the vertical direction are equal to 0, and the sum of moments around any point is equal to 0. So let's look at the first equation. The sum of forces is equal to 0. The only force or horizontal force we have is R3. So R3 or negative R3 is equal to 0. That's the first equation. The second equation, P is acting downwards, so negative P. R1 and R2 are acting upwards, so we have R1 minus P plus R2 is equal to 0. The third equation is taking the moment around this point here. We have negative P multiplied by A plus R2 multiplied by the length L is equal to 0. And so, solving these equations, we find the reactions. R1 is equal to P multiplied by B divided by L. So this is the first reaction. The second vertical reaction, R2, is equal to P multiplied by A divided by L. And the third reaction, R3, equals 0. Now we're going to use the virtual work method to find those reactions. So first we're going to utilize an arbitrary virtual displacement. So we're going to assume that the displacement of the beam is perturbed and the additional displacement is y star, a virtual displacement that is equal to y1 star, which is the displacement, the vertical displacement of this point, plus x1 sine theta star, where x1 is the horizontal displacement. So the vertical displacement here is equal to the displacement of the first point plus x1 sine theta star, where theta star is the slope of the beam. We also are going to assume that the beam has moved horizontally at displacement x1 star. And now we're going to apply the equation that the external virtual work is equal to 0 during the application of this displacement. The forces acting on the beam are R1, P, R2, and R3. Each force is multiplied by the corresponding virtual displacement. R1 acting upwards, multiplied by y1 star, P acting downwards, multiplied by y2 star, which is upwards, and that's why we have the negative sign, plus R2, which is acting upwards, multiplied by the corresponding displacement y3 star. The fourth force is R3, R3 is acting according to the arrow here. The displacement x1 star is in the opposite direction, so minus R3 x1 star. Y2 star is in fact equal to y1 star plus the length a multiplied by sine theta star, and so we substitute for y2 star with this. Similarly, we substitute for y3 star with y1 star plus L sine theta star, and so we get this new equation. After rearranging, we can get three distinctive terms. The first term is everything that's multiplied by x1 star. The second term is everything that's multiplied by y1 star. And the third term is everything that's multiplied by sine theta star. Because the virtual displacement is arbitrary, and the principle of virtual work states that it applies for any choice of the arbitrary virtual displacement field, we can choose any values for x1 star, y1 star, and sine theta star. And because we can choose any values, we can choose, for example, x1 star is 1 and the rest are zeros, y1 star is 1 and the rest are zeros, and so on. So we end up that every term has to be equal to 0. And so we end up with the three equations again. R3 equals 0, R1 minus P plus R2 equals 0, negative PA plus R2L is equal to 0, which are the three equilibrium equations. And so we get the same solutions, and this example indeed shows that the principle of virtual work is actually equivalent to the equilibrium equations. Sum of forces equal 0.